In this video, we'll do two exercises. So we'll design an RST controller without and with integrator. We'll do this for this process. So this process is 0.2 s plus 1 to the power 2 over s times s plus 1 to the power 3, and there is a delay of 1 second. And in the second exercise, we'll treat this case 1 over s plus 1 to the power 4 and then exponential of minus s, so again a delay of 1. And in both cases, these are the specifications, right? So settling time of 20 seconds, so this is equivalent to saying that the closed loop time constant is 4 seconds, an overshoot of 17%, so this is a damping ratio of 0.5, and we'll use a sampling interval of 1 second. So of course, when you're done, there is a multitude of exercises that you can do. You can change the process, you can change the specification, and you can change the sampling time. So what you should do when you follow this video is maybe push the pause button at some time and try to do the design by yourself and see if you manage. If you don't, well, you come and have a look at the solution, okay? But this should become a drill, because you know that you'll have an exercise like that at the time of the exam. So let us start with the first exercise. The process is encoded over here. So we use the s variable, and what you can see here is that everything is made parameterizable, but it is indeed this process that is used. Here are the specifications, and the specifications are in terms of the closed loop time constant. So if you multiply this by 5, you see indeed that the settling time is 20 seconds, Ts is equal to 1. We need the zero order hold equivalent description, so this is obtained by using the command C to D. It is not necessary to put the argument ZOH. You can, because if you use C to D without argument, it is the zero order hold equivalent description that is obtained. So what we need to do first is obtain the B polynomial and the A polynomial. So let's have a look. So maybe we first have to run the code, and then we can have a look here. So this is the process that has been obtained using the command C to D. You have to pay attention to this one. So we have to see it as 1 over c. So actually you should take this denominator and multiply it by z. So the denominator is a 5th order polynomial and the numerator a 3rd order polynomial. If you use this command, you can obtain the numerator, and if you're using this command over here, you obtain the denominator. And you can see here that this z minus 1 has not, or 1 over z has not been taken into account. So it's very important that you take this one over here and put a 0 at the back, so that you have a 5th order polynomial. In order to have a numerator of the same length, you'll have to take this one and put a 0 in front. If we go and have a look, this is indeed what we do. We put a 0 at the back here to obtain this 5th order polynomial, and a 0 in front to make sure that b of z has the same length as a of z. So let us check that. So this is a of z. You can see that it is this one times z and b of z. So it is this one. Yeah, and it is indeed a 3rd order polynomial. Well, the next thing that we have to do is factor b of z in b plus and b minus, and for that we need to use the command roots to obtain the roots of b of z. So let's have a look. So here they are. Clearly you can see that this one is outside the unit circle, so this root is clearly outside the region of good performance. This one here is at the left. So if we draw the unit circle, so it's located somewhere over here. So this kind of root is kind of limiting because it's close to the origin, right? So you could put it in B plus because its influence is going to disappear rather fast. Here we have decided to put it in B minus because if you compensate it, you'll have it in the denominator and this will cause this oscillating behavior. It is close to zero, so it will disappear, but we have chosen here to, well, not to put it in the denominator of the controller. So the two first roots will be in B minus Z, and this one will go to B plus Z, right? So, and this is indeed what we have done. If you look at the code, B plus is monic, so it's Z minus the third root, and B minus is Z minus the first root times Z minus the second root, but we have to adapt. This one is not monic, but we have to adapt in such a way that B plus times B minus is B of Z. So we have to multiply by the coefficient that is in front of the highest power in the polynomial B of Z. If we go and have a look, and we look at B of Z, indeed this coefficient is the third one, right? So we have to multiply B minus by this coefficient. We also have to adapt the length. It's always the length of B minus that needs to be adapted. This is because we have to construct later this Sylvester matrix, and this is really important. We have to adapt the length in such a way that when you compute the product B minus B plus, it has the same length as B of Z, and therefore also the same length as A of Z. Let's check that. So this is B of Z, B plus, B minus. You can see here in front this coefficient. This one is not monic, this one is monic. Now we can compute the products. You can see that this is equal to B, okay? So obviously it has also the same length as B, and it has the same length as AZ, as you can see over here. Well, the next thing that we have to do is to construct the reference model T desired, the closed loop desired transfer function, and it's BMZ over AMZ, right? BMZ is, well, B minus, so we keep in our desired transfer function at the numerator these roots that are not in the region of good performance, and we adapt by this Bm prime, right, that in most cases is a constant, and it will be in our case as well. So we have that the degree of A is 5, the degree of B is 3, so the delay in the process is 2. The degree of B plus is 1, the degree of B minus is 2. So we know now that the degree of Bm is 2 as well. It's the degree of B minus. We have to have the same delay in our reference model than in our process. So we know now that the degree of the polynomial AM is 4. So what we do now is take our specifications in terms of zeta and closed loop time constant, and we compute the natural frequency, right? And then we can compute the two main poles, and the two main poles are R0 exponential of plus minus j omega 0. So we'll take AM of z will be z minus R0 exponential of j omega 0 times z minus R0 exponential of minus j omega 0. We need a fourth order polynomial, so what we'll do is put two fast poles. So we'll use z minus 0, so that's the fastest pole that you can have, squared, right? So this one here is z squared minus 2r0 cosine omega 0 plus r0 squared, right? So this one you have over here, and this part over here, z squared, you have over here. So now we have AM, we have B minus, right? And we need to construct BM, but we know that the desired transfer function evaluated in z is equal to 1 is 1. So this is really going to be B minus in 1 times BM prime divided by AM evaluated in 1, right? So in order to make sure that the static gain is 1, well, we need to take BM prime as AM evaluated in z is equal to 1 over B minus evaluated in 1, and this is what we do over here. Once we have BM prime, right, we can compute BM, okay, the numerator as follows, right? So now we have the numerator polynomial and the denominator polynomial, and what we should do is, of course, check if everything is okay. So what you can do then is use this command here. So this one here will construct a system with transfer function Bm over Am with sampling interval Ts, and then we take the step. And if we do this, well, this is what we obtain, okay? And this seems to be okay. 17% overshoot, zeta is equal to 0.5, and the settling time is roughly 20 seconds. You should always check that your desired reference model is correct before you go any further. We can also clearly see here that the static gain of the reference model is indeed 1. What we have done so far is in common whether you have an integrator or not. So here we first do a design without integrator, and what you can now do is compute the degree of the observer polynomial A0, the degree of RB, and the degree of S, and this is what you obtain. You can see here that we decide to put all the zeros at the origin for the observer polynomial, but clearly here you should also take other types of design, especially if you're working on a real process. You can play with this observer polynomial to test robustness. So here we see that we have 9 parameters, right? So what we have to do now is construct the Sylvester matrix. So remember, the Diophantine equation that we have to solve here is A R bar plus B minus S is equal to AM A0, right? So this one is going to produce C. This is done over here. The degree of this one is 3, and the degree of this one here is 4. Okay, so we have to construct, so degree 3, degree 4, sum 7 plus 2, 9 parameters. So this is why we initialize the Sylvester matrix to a 0, 9 by 9 matrix. So we'll have 4 parameters for R bar and 5 parameters for S. So this is this construction here where we use 4 times AZ, we use the transpose, and we do this shift operation. So we do this degree of 3 plus 1 4 times, and for S we have to use B minus over here, and we have ensured previously that B minus has the right length, and we have to do this, use it 5 times, each time shifting by 1 element. Go and have a look in the previous video. I've made a drawing of this, but we'll check this structure that you should have in M, the Sylvester matrix, later. So now we have the system of equation M, number of parameters. There are 4 over here, 5 over here, is equal to, well, a column vector with the coefficients of C. So you can obtain the parameters simply by solving this system of equation. This is how we do it, since we had a course on linear algebra. The 4 first parameters are going to lead to R bar. The last 5 are S. S you obtain directly from the Diophantine equation. R, well, R of Z is R bar, the one that you obtain from the Diophantine equation, times B plus, right? And T of Z is the product A0 times BM prime over here. And this is how we obtain the 3 relevant polynomials from the RST controller. What you can do is have a look at the matrix M. Since the matrix M is a bit large, it's difficult to see the structure, but you can kind of see it's correct. There are commands around that will present it in a neat fashion, and here you can clearly see this, well, AZ that is shifted each time, and here you see B minus that is shifted each time. So you should really check if your matrix is indeed correct. Well, then of course you can compute the transfer functions, the closed loop transfer functions, R to Y, R to X, the output of the controller, and we'll load disturbance to Y and see what happens. Here we have also plotted the reference model. And here you can see the step response. As you can see, well, the actual response and that of the reference model are one upon another, so you cannot see the difference. We meet, of course, the specifications in terms of overshoot, settling time, and of course the static gain is 1. This is the controller output, and this is the load disturbance. We have had a design with LC is equal to 0. There is no integrator in the controller, so clearly we are not able to reject a load disturbance. So we can now have a look at a design on the same process but with an integrator in the controller. Everything that has been done up to the design of the closed loop reference model is the same. The only thing that changes here is, since that LC is equal to 1, this is going to have an impact on these degrees, right? The degree of A0 is now 5. We choose this observer polynomial, so we put here all the roots at the origin. So clearly this is not the best design. If you're working on a system, you should experiment with observer polynomials and test if, well, this is going to improve the robustness. And this is really important if you're working on an actual process. Here, the degree of R bar prime is 3 and the degree of S is 5. So we have 10 parameters over here. The Diophantine equation that we have to solve is AZ, Z minus 1 to the power LC, so 1 here, then R bar prime, so this is going to be a solution of the Diophantine equation, B minus S is equal to AM A0. So this is C, the C polynomial that is constructed over here. This one here now has a degree 3, okay, and this one has a degree 5. So 5 plus 3 plus 2, there will be 10 parameters. We have to initialize M as follows, right? So now we have again to construct this Sylvester matrix, and for that we're going to use this polynomial AIZ. It's simply AZ times Z minus 1 and it's computed over here. So we'll use, since there are 4 parameters over here, 3 plus 1, the degree 3 plus 1, we have to use this one transposed 4 times, and each time we shift. Then we have to use B minus, well, 6 times, because there are 6 parameters in S, and again we use this transpose of B minus and we shift. So of course what we'll do is, well, check this matrix to see if it has the right structure. So this is how we obtain the parameters. I'm not going to go into the details, and the 4 first parameters are related to R bar prime, and the 6 last parameters, and because it's 5 plus 1, are related to S. S you obtain directly from the Diophantine equation. R, well, you need to take, as is shown over here, well, it's R bar, this is not right, so R bar prime times B plus times Z minus 1, and well, T is obtained as usual, A0, the observer polynomial, times Bm prime over here. And this is how we obtain the 3 relevant polynomials. So again, we should check the structure of our matrix M. So let's look at M. You can kind of see here that indeed we have the right structure. There are commands around that will make this check a little bit easier, as you can see. Well, again, we can compute the transfer functions, the 3 transfer functions, using the same commands as before. So these are the 3 responses. The response to a set point, and as you can see, we meet the specifications. There is no difference between the, well, desired response and the actual response. This is of course because we are working on a process that is also the one that we've used for design. This is the controller output, only very little difference, but now we are able to reject a load disturbance. And this is of course because we have introduced in our controller an integrator. We are able now to reject a step-like load disturbance. So what we'll do now, we'll take the second system, 1 over s plus 1 to the power 4 times the exponential of minus s, and we'll use the same specifications as before. You should be able by now to do this design by yourself, so try first and come and have a look if you end up with problems or if you succeed and if you want to compare. So this is the Matlab code for this second example. This is the process. We have introduced the Matlab variable and the following parameters, so you're really working on this process over here, and these are the specifications. The sampling time is 1 second. So as usual, you need to obtain the zero order hold equivalent discrete description. You can use the command C to D, and what you have to do now is obtain B of Z and A of Z. So let's, well, maybe first run this code and then have a look at the process. So again, we have this Z minus 1 over here, so pay attention. The denominator is of order 5. It's this one multiplied by Z, and the numerator is, well, indeed third order. If you, this is the numerator and this is the denominator, right? You can see here that it's a fourth order polynomial, and we can see here that the denominator is really a fifth order. This is coming from this delay in the continuous time system that has given rise to this Z minus 1, but you should really put it in the denominator. So we need to take this one and put a 0 in the back because you multiply by Z. Since the numerator has to have the same dimension, you'll have to take this one over here and put a 0 in front, and you can see here that this is really what we are doing. So the next thing that we have to do is to take B of Z and factor it as B plus and B minus. For that we need to compute the roots of this numerator polynomial. Let's do this in Matlab. So roots, this is what you obtain, right? So the first one, there is no discussion. It is certainly not in the region of good performance. The second one is located over here. So this is more or less the second one, and this one is very, very close to the origin. So this one is problematic, but this one is problematic as well. It's too close to Z is equal to minus 1, so here really there is no discussion. We have to put both of them in B minus. If we don't, we'll have them, well, this will produce a unstable pole zero cancellation, so this would be catastrophic. But this one, we would have it in the denominator, and this would produce this oscillating behavior, and since it's too far from the origin, it would last too long. So this one goes into B minus. This one is still negative, but it's so close to the origin that you can put it in B plus, right? So let's see and have a look at what we have done. And here you see that indeed the third root is in B plus. B plus is Z minus the third root. B minus is Z minus the first root times Z minus the second root. And then we have to make sure that when we multiply B plus and B minus, we have B of Z, and for that we have to make sure that we multiply B minus by the coefficient that is in front of the coefficient of highest power of Z in B of Z. Let's go and have a look, and this is indeed the third coefficient. So this is why here we multiply by this coefficient, right? So what we have to check now is that this is B of Z. We can have a look at B plus. b minus, and then we can multiply both of them, and as you can see here I have the same result, and it's the same length as b of z, and it is also the same length of a of z. So you have to do these checks before you go any further. We have checked that b plus times b minus is bz, and here it is indeed the case, but it is also because we have extended b minus, as you can see over here. So extend b minus with a number of zeros that is such that when you multiply b minus and b plus, you obtain a vector of the same length as b of z, which is also the same length as a of z. So now we have to design our reference model. T designed, it's bm over am, and bm is really, it's b minus, so this is what you keep from the numerator of the process, so those zeros outside the unit circle, times some constant bm prime, right? So the degree of bm is the degree of b minus, it's 2, right? Here the delay in the process is 2, it's 5 minus 3, right? And in the designed reference model we are going to use the same delay to avoid problems with causality of the controller. So to have the same delay, we'll fix the degree of am to 4. You can see now that, well, the degrees over here are exactly the same as in the other example, but this is pure luck because the process is completely different. Of course, in other situations you could have very different things, right? So in order to have something different, what you could do is design a RST controller for a process that is slightly different. So for instance, in the denominator you have s plus 1 to the power 3 or to the power 5. What is important is that, of course, you understand how to construct things. From the specifications, what you can do is construct the two main discrete time poles, right? So now we know that AMZ will be Z minus R0 exponential of J omega 0 times Z minus R0 exponential of minus J omega 0. This is Z squared minus 2R0 cos omega 0 Z plus R0 squared. This is second order. We need a fourth order. So we have to multiply here by, well, something with fast poles. So alpha 1 Z minus alpha 2. And typically to have fast poles, we'll set simply alpha 1 is equal to alpha 2 is equal to 0. And this then becomes Z squared. Okay, so these are fast poles and they will not interfere with the main poles. And this is how you obtain, well, Z square times Z square minus 2R0 cosine omega 0 Z plus R0 squared. And this is the AM. We know that the desired closed loop transfer function, the reference model, when evaluated in Z is equal to 1, should produce 1. This is going to be B minus 1 BM prime over AM 1. So BM prime is equal to AM evaluated in 1 divided by B minus evaluated in 1. You can simply implement that by this operation here. This one here evaluates the polynomial AMZ in z is equal to 1. Once you have bm prime, you can compute bm, and you're now ready to test the desired closed loop response, the reference model. So let us test this reference model, and this is what we obtain. So you can see here that the specifications are met, 17% overshoot. We have a static gain of 1 and a settling time of 20 seconds. Again, check your reference model before you go any further. So again, what we have done so far is in common for a design with or without integrator. So from now on it changes. So we'll start without integrator. LC is going to be 0. So now you can obtain the degrees. So the degrees of the observer polynomial, 4. Here it is. Here again we have chosen to put every root at the origin, but this is not necessarily so. Investigate, for instance, in your laboratory assignment what happens if this is not the case. Clearly it will not have an influence on the closed loop set point response, but it will influence the load disturbance, right? And then we can obtain the degree of the polynomial r bar and the degree of s. So we'll have 3 plus 4 plus 2, 9 parameters. The Diophantine equation that we have to solve is a r bar plus b minus s is equal to am za 0. This is c of z, and it is computed over here. This one is of degree 3, this one of degree 4. So we'll have 9 parameters. 3 plus 4 plus 2. Polynomial of degree 3 is described by 4 parameters and one of degree 4 by 5 parameters. So indeed we have 9 parameters. So we'll have a system of equation with 9 equations and 9 variables. So this is how we initialize the Sylvester matrix. So there are 4 parameters in RB. So we'll have to use A transposed 4 times using the shift operation, and we'll do the same for B minus transpose, and we'll have 5 parameters, so we'll have to use it 5 times, each time shifted, and this is going to produce the Sylvester matrix. Then we can compute the parameters. The first 4 ones are for R bar, and the last 5 ones are for S, right? S is obtained directly from the Diophantine equation, and R is computed from R bar by multiplying by B plus, and T as usual is simply A0 Z times Bm prime. What we can now do is compute all those transfer functions and look at the step responses. And as usual, we look at the Sylvester matrix to see if it has the right structure, and this is indeed the case. So this is the set point closed loop response. As you can see, we meet the specification, and the actual output is equal to the reference output. This is because we work on the actual system, which is also the model that we have used for the design. This is the controller output, and this is the response to a load disturbance. We do not have any integrator in the controller, so we are not able to reject a load disturbance. We can now have a look at the design with an integrator. So LC is equal to 1. The design of the closed loop reference model is of course the same. What will change is what is over here, the degree of the observer polynomial. Here you have the observer polynomial. Again, you can investigate what happens if you put other routes than 5 routes at the origin. This will influence the robustness of the system, of the controller on the actual system, and it will also influence the load disturbance response. So here we have a polynomial r bar prime of degree 3 and a polynomial of degree s of degree 5. So we'll have 5 plus 3 plus 2, 10 parameters to obtain from our system of equations. Well, the Diophantine equation that we have to solve is a z minus 1 r bar prime z plus b minus times s z is am times a0. This is c of z, and it is computed over here. Okay. In this Diophantine equation, we'll use ai z in the construction of our Sylvester matrix. This looks a bit mysterious to you? Again, have a look in section 1. This has been introduced in this early section 1. So this is computed over here. We had a polynomial of degree 3 here, of degree 6 here. So what we'll have is, no, this is not degree 6, it is degree 5. I can see here because we have 10, so the number of parameters is the degree of r bar prime plus the degree of s, right, plus 2, and this is indeed 10, and this is how we initialize our Sylvester matrix. This one has degree 3, so 4 parameters are used to describe r bar prime, so we'll have to use this one 4 times transposed, and we'll have to introduce it in the matrix by each time shifting, right? So this is done 4 times, and here we'll have to do it 6 times because in S there are 6 parameters, so we'll have to use b minus, transpose it, and introduce it in the matrix M column by shifting, and this is going to produce this structure in the Sylvester matrix. So now we have the system of equations where we have the parameters over here. These are the parameters of r bar, there are 4 of them, and here you have the parameters of s, there are 6 of them, and then this is equal to, well, the coefficients that you have in the c polynomial. So to solve this, you do this in the proper way, as we have seen in the course of linear algebra. R bar is obtained by taking the 4 first parameters, and s is obtained by taking the last 6 parameters. Then we compute rz by taking r bar prime, multiplying by z minus 1 and multiplying by b plus, and s is simply coming from the Diophantine equation, and t of z is really a0z bm prime. So you can see that it's always the same thing that comes back. What we can now do is compute the 3 closed loop transfer functions and look at the step responses: set point to output, set point to control output, and load disturbance to output. As usual, we check the matrix M. It's difficult over here with this command, but still it is possible to see, and with this one it becomes a little bit easier. Here you see the closed loop responses at the sampling instance, since you are working in Matlab. If you want to see the intersample behavior, of course you have to go to Simulink. So this is the set point step response. So we see that the output meets the specifications. This is the output of the controller for this set point step response, and what we see over here is the load disturbance step response. We're seeing that the controller is able to reject a step-like load disturbance because everything comes back to 0, and this is kind of obvious because we have had a design with LC is equal to 1, so there is indeed an integrator in the controller. So make sure that you understand this, and so how the number of integrators in the controller affects the step response in closed loop, and set point step response and the load disturbance step response.